A car with 60,000 miles on the clock pulls away from a stoplight on an ordinary Tuesday morning. Nothing about the moment feels dangerous. The driver has coffee in the cup holder and a podcast playing through the speakers. And then, without warning, something inside the engine lets go. A knock, a shutter, a dashboard suddenly lit up like a slot machine. The car that was supposed to last 200,000 miles is now sitting on the shoulder with smoke curling out from under the hood, and the owner has no idea why. This isn't a rare story anymore. It's happening across brands that people trust with their lives and their savings, in engines built by companies with decades of engineering pedigree behind them. And when you actually dig into why, the answer isn't a scandal, and it isn't sabotage. It's something far stranger. It's a story about how the pursuit of perfect efficiency quietly erased the safety net that used to protect every engine on the road, and how engineers in Japan, chasing smaller, lighter, and more fuel-efficient designs, ended up building machines with almost no room left for anything to go wrong. To understand what's happening now, you have to understand what engines used to be. For most of the 20th century, an engine was, by modern standards, wildly overbuilt. The metal was thick. The tolerances were loose. The oil was heavy and forgiving. If you skipped an oil change, if you let the engine run a little hot, if a bearing wore down slightly faster than it should have, the engine didn't care. There was slack everywhere. Slack in the clearances between moving parts, slack in the oil's ability to protect metal surfaces, slack in the sheer mass of iron surrounding every moving component. That slack was never advertised as a feature. Nobody put generous tolerances on a sales brochure. But it was the quiet reason those old engines could survive decades of neglect and still turn over on a cold morning. That slack is disappearing, and it's disappearing on purpose. Engineers everywhere, but especially in Japan, where fuel efficiency and emissions compliance have shaped automotive design for generations, have spent the last 20 years chasing a single goal above almost everything else. Squeeze more distance out of every drop of fuel, while meeting emission standards that get stricter with each passing year. That goal sounds simple. In practice, it required rethinking nearly every part of how an engine is built, and every one of those changes quietly removed a little more of the margin that used to keep engines forgiving. Start with the oil. If you look at what a car from the 1990s called for on its dipstick cap, you'd likely see something like a 10W30 or 10W40. A relatively thick, heavy-bodied oil that clung to metal surfaces and left a durable film behind. Walk into a dealership today, and the recommended oil on many models is a 0W20. And on some of the newest Japanese-engineered vehicles, it's a 0W16, an oil so thin it would have been considered dangerously light for an engine just 2 decades ago. The reason engineers moved to these thinner oils is straightforward. Thinner oil creates less internal friction, and less friction means the engine works a little easier and burns a little less fuel. Multiply that tiny gain across millions of vehicles and hundreds of millions of miles, and it becomes a meaningful number on a fuel economy report that automakers are legally required to meet. But thin oil only works if everything else around it is engineered to match. To keep an ultra-thin oil film from simply squeezing out from between moving parts, engineers had to shrink the clearances those parts ride in. The gap between a spinning crankshaft and the bearing that cradles it, the space that oil fills to keep hardened steel from ever touching itself, has been tightened dramatically compared to older designs. In many modern engines, that gap is now filled by an oil film measured in microns, thinner in places than a human hair. As long as that film holds, the engine runs smoothly, because the metal surfaces never actually touch each other. They float on a cushion of pressurized oil. But the moment that film breaks down, because the oil has overheated, because it's aged past its useful life, because it's been diluted by unburned fuel, there's no cushion left to absorb the mistake. Metal meets metal at several thousand revolutions per minute, and that contact is the beginning of a bearing failure. This is where oil change intervals become part of the story. Automakers have steadily extended the recommended distance between oil changes from the old standard of around 3,000 miles to 5, then 7.5, and now commonly 10,000 miles on new vehicles, with some manufacturers pushing toward 15,000. On the surface, this looks like proof that oil technology has simply gotten dramatically better. In some ways it has. Modern synthetic oils are more stable than the oils of decades past. But the engines running on that oil have also become far more demanding of it. Turbocharged, direct injection engines run hotter than the engines those old intervals were designed around, and some fuel inevitably seeps past the piston rings during direct injection, thinning and contaminating the oil below. The oil in a modern engine is being asked to survive a more hostile environment for a longer stretch of time, and the dashboard indicator that tells drivers when to change it isn't actually measuring the oil's condition. On most vehicles, it's an algorithm estimating oil life based on driving patterns, cold starts, and mileage. It's an educated guess, not a direct reading. And it has no way of knowing that the oil sitting in the engine at 9,000 miles has already lost a meaningful portion of the protective qualities it started with. That thinning, aging oil becomes especially dangerous once you understand how. Many modern engine components depend on it functioning perfectly. Cylinder deactivation is one example. It's a technology that allows an engine, most often a larger one, to shut down some of its cylinders during light load driving, like cruising on the highway, in order to save fuel. It relies on small hydraulic lifters that use oil pressure to collapse and release valves on command, sometimes cycling on and off thousands of times during a single drive. When the oil supplying those lifters is clean and at the right pressure, the system works invisibly. When the oil has degraded, the timing of those lifters can go wrong, causing them to stick or fail to reseat properly. A stuck lifter gets hammered by the camshaft it's supposed to glide against, and the resulting damage often means an expensive repair involving the cylinder heads and sometimes the camshaft itself. It's a feature designed to save drivers a small amount of money at the pump, riding on a system that has very little tolerance for anything less than ideal oil. Direct injection introduces its own version of this trade-off, and it centers on carbon rather than metal. For decades, fuel injectors sprayed gasoline into the intake port just before the valve, and that spray of fuel acted as a natural solvent, washing away deposits before they could build up. When engineers moved to direct injection, spraying fuel straight into the combustion chamber at extremely high pressure for more precise combustion and better efficiency, they gained real performance benefits. But they also removed that self-cleaning effect. Fuel no longer touches the back of the intake valve, while oil vapor and combustion byproducts continue to drift across it. Over time, and often by around 60,000 miles, this creates a hardened carbon buildup on the intake valves that can disrupt airflow, cause rough idling, hesitation on cold starts, and a gradual, hard-to-diagnose loss of power and fuel economy. Cleaning it isn't as simple as adding a fuel additive, since the fuel never reaches those deposits in the first place. Technicians typically have to remove the intake manifold and use a specialized abrasive media, often crushed walnut shells, to physically blast the carbon away. Some manufacturers anticipated this problem and now run both direct and port injection together, using the older style injector occasionally just to keep the valves washed. But a large number of engines built without that dual system are out there right now, quietly accumulating deposits with no built-in way to clean themselves. Carbon buildup and abrasive combustion byproducts feed into another problem that would have sounded unfamiliar to a mechanic 30 years ago: timing chain stretch. Timing chains were traditionally designed to last the entire life of an engine without any scheduled maintenance. But direct injection tends to produce more soot than older combustion methods, and that soot circulates through the oil as fine, abrasive grit. At the same time, in the pursuit of lighter, more efficient engines, timing chains themselves have often become thinner and narrower than the robust chains used in older designs. A lighter chain running in oil that carries more abrasive particles for a longer interval between changes wears at every link and roller. That wear doesn't stretch the metal itself, but it accumulates as slack across the length of the chain, gradually shifting the timing relationship between the crankshaft and camshaft. In mild cases, this shows up as a rough idle or a warning light. In severe cases, the chain can skip a tooth on its sprocket, and in an interference engine, where the pistons and valves occupy the same space at different points in the cycle, that loss of synchronization can cause a piston to collide directly with an open valve. The damage from that kind of event is often severe enough to end the engine's life outright. Industry oil standards have actually been updated in recent years specifically to address chain wear, including formal testing for how much a timing chain stretches under real operating conditions, a sign of just how common this failure mode had become. Perhaps the most dramatic failure tied to all of this is a phenomenon called low-speed pre-ignition, something that barely existed as a named issue before the widespread adoption of small, turbocharged, direct injection engines. It tends to occur in a very specific and very ordinary situation, pulling away from a stop with a heavy foot on the accelerator, at low engine speed and high load. In that moment, cylinder pressure climbs rapidly while the piston is still moving slowly, creating conditions where a stray droplet of oil or fuel residue clinging to the cylinder wall can ignite on its own, before the spark plug fires in its normal, controlled sequence. That early uncontrolled ignition creates a pressure spike far beyond what the engine was designed to handle in that instant, and it can happen in a fraction of a second. The resulting shock can crack piston ringlands, damage the piston crown, or destroy bearings, sometimes in a single event rather than through gradual wear. Fresh, properly formulated oil is genuinely effective at resisting this kind of pre-ignition, which is part of why current oil specifications include testing for it. But as oil ages toward the far end of an extended service interval, its ability to resist this failure mode fades, tying the story back once again to something as ordinary as how long oil sits in an engine before it's changed. None of this means every driver should expect their engine to fail, and it would be inaccurate to suggest that modern engines are simply bad. The vast majority of them run reliably for hundreds of thousands of miles when properly maintained. What's changed is the margin for error. Engineers, particularly in Japan's automotive industry, have spent decades refining engines to extract remarkable efficiency and performance from smaller displacements. And, in many respects, that engineering has been genuinely impressive, allowing four-cylinder engines to produce power that would have required a six-cylinder engine a generation ago. But that achievement came from removing slack, not adding it. Every one of the design choices behind it, thinner oil, tighter clearances, direct injection, downsized turbocharged engines, was made deliberately in pursuit of real and measurable gains in efficiency and emissions. Individually, each trade-off is defensible engineering. Together, they've created engines that perform beautifully under ideal conditions and have very little tolerance left for anything less than ideal, whether that's slightly extended oil changes, lower quality fuel, or simply the ordinary, where that accumulates over a decade of driving. There's another layer to this story that rarely gets talked about, and it has to do with how engines are actually put together on the assembly line. Even the best design on paper can be undone by something as small as a stray piece of machining debris, a tiny metal particle left over from cutting and shaping internal oil passages during manufacturing. In an older engine, with wide oil galleries and generous clearances, a speck of debris like that would likely just get flushed along with the oil and cause no real harm. In a modern engine, where oil passages are narrower and clearances are measured in microns, that same speck of debris can lodge exactly where it shouldn't, at a main bearing supporting the crankshaft, for instance, and slowly grind away at a surface that was never designed to tolerate any contamination at all. This is part of why some manufacturers have had to revisit their own assembly processes over the years, adding extra cleaning steps to oil passages or switching to harder-bearing materials, not because the original design was fundamentally flawed, but because the tolerance for manufacturing imperfection has shrunk right alongside the tolerance for maintenance imperfection. When your margin of safety is measured in microns, there's no longer a meaningful difference between a design flaw and a manufacturing flaw. Either one can produce the same result. It also helps to understand why so many of these failures feel like they come out of nowhere. A bearing that's slowly wearing doesn't usually announce itself. There's no dashboard warning for a protective layer thinning out gradually inside an engine. No code that trips the moment a timing chain accumulates a little extra slack. The wear tends to happen in silence mile after mile, invisible to both the driver and the diagnostic systems monitoring the car, right up until the moment the film finally gives way, often during a moment of real load, like merging onto a highway or climbing a steep grade. That's part of what makes these failures so unsettling to the people who experience them. The car seemed perfectly fine the day before. In reality, the process had likely been building for a long time, quietly consuming the tiny margin the engine had left. Even engineers working on some of the most ambitious projects in the industry have run into this same wall. Consider the years-long effort by one Japanese manufacturer to build an engine capable of physically changing its own compression ratio while running, adjusting itself in real time between a low compression setting for power underboost and a high compression setting for efficiency while cruising. It's a kind of achievement that takes decades to perfect precisely because it's mechanically so difficult, relying on a system of links and an actuator that constantly shift the geometry connecting the piston to the crankshaft. Every one of those links rides on its own precision bearing, and every one of those bearings depends on that same razor-thin film of oil to survive. Even genuinely groundbreaking engineering, in other words, is still bound by the same underlying physics as the simplest engine on the road, and still exposed to the same risk if oil quality or clearances fall even slightly outside their intended range. It's worth being clear about something here, because this topic tends to attract more alarm than the facts support. Manufacturers do issue recalls and conduct investigations when specific failure patterns emerge, and that process, while frustrating for the owners affected, is generally a sign that the system for catching design or manufacturing flaws is working as intended. It doesn't mean every engine of a given type is destined to fail, and it doesn't mean modern engineering is fundamentally broken. What it does mean is that maintenance matters more now than it used to, not less. Following manufacturer-recommended oil types and intervals, rather than defaulting to the longest interval offered. Paying attention to unusual noises or rough idling instead of dismissing them, and choosing quality fuel and oil products all make a real difference in engines with this little margin built in. The forgiveness that used to be baked into the hardware now has to come from the person behind the wheel. So here's the real takeaway. The story of failing modern engines isn't a story about greedy corner cutting or reckless design. It's a story about engineering pushed right up to its limits in service of efficiency and environmental goals that society genuinely asked for: cleaner air, better fuel economy, smaller carbon footprints. Getting there meant trading away the enormous safety margins that used to define how engines were built, and replacing them with precision so exact that there's almost no room left for anything to go wrong. When everything lines up, oil quality, maintenance schedules, driving habits, these engines are remarkable machines. When something in that chain slips, even slightly, the consequences can be sudden and severe in a way older, cruder engines simply weren't capable of. Understanding that trade-off doesn't just explain why headlines about engine failures keep appearing. It changes how you think about the engine sitting under your own hood right now, and what it actually takes to keep something that precise running the way it was designed to. If you found this breakdown useful, let me know in the comments which trade-off surprised you the most, and stick around, because the next video digs into exactly what a smart maintenance routine looks like for an engine built this way.